At midnight, December 2nd, 1984, the worst industrial accident in history occurred at a U.S.-owned pesticide manufacturing plant in Bhopal, India.
It was a reactive chemical accident. Methyl isocyanate is highly reactive with water.
Dennis Hendershot is an industry consultant in chemical process safety and has toured the now abandoned Bhopal accident site.
Water got into the storage tank somehow. Water reacted with the methyl isocyanate, causing the release, which killed thousands of people.
Thousands more died in the aftermath of Bhopal, and tens of thousands continue to suffer today. But Bhopal also brought about change.
Bhopal totally changed the understanding of potential process safety hazards in the chemical industry.
Bhopal spurred Congress to require new OSHA and EPA regulations covering chemical process safety. And Congress established the CSB to independently investigate chemical accidents.
There have been many positive changes in chemical industry process safety since 1984, when the Bhopal nightmare occurred. But the CSB has found that accidents involving reactive chemicals still occur all too frequently and often with tragic results. This video focuses on 4 major accidents investigated by the CSB, accidents that demonstrate what happens when reactions run out of control, resulting in fires, explosions, and toxic releases that cause death, injury, and environmental damage.
Such an accident unfolded on the morning of January 31, 2006, when a vapor cloud exploded at the Synthron acrylic polymer manufacturing plant in Morganton, North Carolina. The blast killed 1 worker and injured 14 others. It destroyed the facility and damaged nearby structures. At Synthron, a seemingly minor increase in the size of a production batch led to a catastrophic explosion. It was a tragic example of what happens when process changes are not managed carefully. Synthron manufactured acrylic polymer coating additives in batches using a 1,500-gallon reactor located inside a production building. The company had produced the polymers for years without serious incident, typically using a 2-step process. In the first step, operators would partially fill the reactor with acrylic monomer and solvent, warm the vessel with steam, and then initiate and run the reaction for up to several hours. Later, in a second step, operators would gradually pump in the remaining acrylic monomer and continue the reaction until the vessel was nearly full of product. Both steps of the reaction generated heat, causing the solvent to boil. An overhead heat exchanger condensed the hot solvent vapors and sent cooler liquid back into the reactor, keeping the temperature and the reaction under control. Shortly before the accident, Synthron received an order for an acrylic product that was 12% larger than the standard batch size. Rather than fulfilling the order by making 2 smaller batches, managers decided to make a single, larger batch and to add all of the extra acrylic monomer during the first step of the process. But this was a critical mistake. Adding the extra monomer all at once more than doubled the heat released by the reaction. The heat exchanger could not condense the vapor quickly enough, and the temperature and pressure inside the vessel began to rise uncontrollably in a runaway reaction. The pressure caused the gasket on a hatch to fail, releasing flammable solvent vapor into the building. Employees heard a loud hissing sound, saw the escaping vapor, and fled the building. 4 workers gathered outside a doorway, where they were joined by the plant superintendent and the plant manager. One of the operators went back inside the building in an attempt to send emergency cooling water to the reactor, but it was too late. The operator returned to his companions outside. Seconds later, the solvent vapor in the building exploded. A worker who had remained inside the lower level of the plant was fatally burned, and 14 others were injured. The building was destroyed. The Synthron accident underscores the need for well-rehearsed evacuation plans. Furthermore, it's critically important for companies to carefully review the effects of making even small changes to reactive process conditions.
Anytime you are rearranging molecules, you have reactive chemistry, and the potential for a reactive chemicals accident is possible.
Dr. Daniel Crowell is a chemical engineering professor and process safety expert.
If you don't mix the raw materials properly, if you add them in the wrong order, if you add the wrong materials into your process, you will lose control of the mass.
In 2002, the CSB completed a comprehensive study of reactive chemical hazards, issuing key safety recommendations to OSHA and the EPA, as well as trade and industry groups. A number of the recommendations have yet to be adopted. The report identified 167 serious accidents involving uncontrolled chemical reactions in the United States over 2 decades, causing 108 deaths and hundreds of millions of dollars in property damage. More than half involve substances not covered under current federal process safety regulations. Between 2002 and 2007, the CSB investigated 10 additional serious reactive accidents and identified many others that caused deaths, injuries, evacuations, or property damage.
Just because the initial screening method says you probably don't have a clearly identifiable reaction hazard, that doesn't mean that that reaction hazard doesn't exist. And you probably need to look into your chemicals and their properties and their reactive nature a lot more thoroughly than you think you need to.
Reactive incidents can occur even when plant personnel are unaware that chemical reactions are taking place. That's what happened at an Augusta, Georgia plastics manufacturing plant in 2001. On March 13, 2001, 3 maintenance workers at the BP Amoco Polymers plant were killed while they were preparing to clean out a tank that held waste plastic. BP Amoco made high-performance nylon by pumping raw materials through a heated reactor and then using an extruder to form the hot plastic into solid pellets. During the first 50 minutes of startup, plastic considered to be unusable was diverted away from the extruder to a 750-gallon waste tank. Steam and gases escaped through a vent in the waste tank, preventing any accumulation of pressure inside. The contents of the tank were allowed to cool down over a period of hours. Workers then opened the cover to remove the waste plastic. On the afternoon before the accident, operators began to start up the process. But there was a mechanical failure in the extruder. While the operators tried unsuccessfully to fix the extruder, the hot plastic continued flowing into the waste tank for an unusually long time. Supervisors eventually aborted the startup, but by then the waste tank had already overfilled with molten plastic. The excess plastic clogged the vent line and the emergency pressure relief line. With the lines and pressure gauge now sealed off, workers would have no reliable way of determining whether the tank was under pressure. As the outside of the waste tank gradually cooled, a hard plastic layer several inches thick formed around the inside surface of the tank. But closer to the center, the plastic still remained hot and molten. Unknown to workers, a slow decomposition reaction was occurring inside the molten plastic. Over a period of hours, the hot plastic molecules were breaking down, forming gas bubbles and causing a dangerous buildup of pressure. Just after 2 a.m., 12 hours after the startup attempt, 3 night shift workers approached the waste tank to clean it out. The workers began to unbolt the cover of the tank. After they had removed half the bolts, the extreme pressure blew the 1,750-pound cover off the tank with explosive force and ejected hot plastic over a wide area. The waste tank recoiled backward, breaking hot oil pipes and creating a vapor cloud which ignited 6 minutes later. 2 of the maintenance workers were killed instantly when the tank cover blew off. The third was pronounced dead on arrival at a hospital. This accident shows how even slow chemical reactions that don't produce any heat can still be hazardous. In this instance, company researchers knew that molten plastic could react to produce gas, but that information was not sufficiently incorporated in the design of the process or communicated to workers.
I think that is one of the main issues. And it's not so much that nobody was aware of that information, but rather that the people who were actually operating the process didn't have the information or didn't have access to it. But somebody, somewhere, even within the same organization, often had that information. So a lot of the problem, I think, is education and awareness.
If you was never in an explosion, it's a horrible feeling. You'll never forget it.
Robert Oliver was a victim of a reactive chemical accident at Morton International in 1998 in Paterson, New Jersey. He and other survivors spoke about the human impact of such accidents at a CSB public hearing on reactive hazards in 2002.
I hope this would help not the United States, but the whole world to be more careful or get more insight on the chemical that they're working with.
I can remember when the fireball hit. I can remember being blown through the air. I can remember the fire. I remember the pain. I lost track of time. I went blank or something. I don't know how I got out of that area.
If my coming here today should save one life or stop somebody else from going through the nightmare I have been living, then it's worth coming here and going through the pain of living it again. Thank you.
The CSB's 2002 study found that over 90% of serious reactive chemical accidents involve hazards that have already been described in the publicly available literature. The board recommended that, to better understand reactive hazards in their processes, companies should consult multiple sources of information and conduct specialized testing if necessary. Collecting adequate safety information and data is especially important when scaling up a reactive process.
On April 12, 2004, the MFG chemical plant in Dalton, Georgia, experienced a runaway chemical reaction. It caused the release of highly toxic vapors into a residential community. The CSB determined that the accident occurred because MFG did not safely scale up a chemical reaction from the laboratory to a large production vessel. MFG was contracted to manufacture 35,000 pounds of a plastics additive called triallocyanurate, or TAC. The company produced 3 trial batches of TAC by reacting alloalcohol and cyanuric chloride inside a small 30-gallon test reactor. In the first 2 tests, operators controlled the exothermic or heat-producing reaction by adding one of the raw materials in small portions. In the third test, all of the chemicals and a catalyst were combined in the test reactor at one time, which was the procedure that MFG later decided to use when scaling up to full production. This third test produced significant heat, but the water cooling jacket around the small vessel was able to keep the temperature low and control the reaction. However, MFG did not realize that compared to the small test reactor, it would be far more difficult to control the temperature in the 4,000-gallon production vessel. The surface area to volume ratio was much lower in the production vessel than in the test reactor. Starting the production process for the first time, operators loaded the large vessel with all of the cyanuric chloride powder and the catalyst. They then added all of the alloalcohol and began mixing the chemicals. To control the temperature, MFG had rented a portable chiller and connected it to the cooling jacket on the vessel. But as soon as all of the raw materials were combined, the reaction began producing heat faster than the cooling system could remove it. The temperature increased uncontrollably, and with all of the raw materials already in the vessel, nothing could be done to control the reaction. The pressure inside the reactor climbed rapidly as the mixture heated. Suddenly, a gasket blew out, releasing toxic alloalcohol and allochloride vapors into the atmosphere. About 10 seconds later, the emergency pressure relief rupture disc burst open, releasing more vapor. Unable to slow the reaction or contain the release, the operators were forced to evacuate to a safe location upwind. The toxic vapors quickly spread into the residential neighborhood east of the facility. Authorities ordered the evacuation of more than 200 families, but the town had not trained or equipped its emergency responders for such an accident. 154 people had to be decontaminated, including 15 police and ambulance personnel. This accident emphasizes the need for emergency responders to be fully prepared for a toxic chemical release. The CSB found the company could have prevented the accident by better understanding the chemical process and knowing how to prevent a runaway reaction.
You don't want to be learning about chemical reactions in a 5,000-gallon vessel. You want to learn about it in a small vessel in the laboratory and understand what's going on so that by the time you get to the large manufacturing vessel, you already know those things. You don't want to get surprises on a large scale.
A large 20,000-gallon reactor will run away a lot faster than a 1-gallon reactor that you're using in the laboratory. And somehow human nature is to believe that larger is slower, and in the case of reactive chemicals, a larger chemical reactor will actually run away a lot faster than a smaller chemical reactor.
Chemical reactions where high temperatures cause decomposition can produce powerful explosions. Few people realize how much destructive energy can be released, as in the following accident at a Mississippi chemical plant. On October 13, 2002, an explosion tore apart a 145-foot distillation tower at the First Chemical Corporation in Pascagoula. 3 distillation towers at the facility separated and purified mononitrotoluene, or MNT, which is used in the manufacture of dyes and agricultural chemicals. The entire facility was shut down for routine maintenance. Plant operators decided to leave 1,200 gallons of MNT inside one tower during the shutdown. This would be safe at normal temperatures where MNT is stable. The heating was shut down on the 2 reboilers by closing the steam supply valves. But unknown to operators, these valves were corroded and worn. Steam leaked into both reboilers over a number of days, heating up the MNT, causing it to break down and become unstable. On the morning of the accident, the temperature inside the tower reached 450 degrees Fahrenheit. A dangerous runaway reaction began, rapidly forming gas and suddenly building up pressure inside the tower. The tower began to rumble, and employees saw material venting quickly from a breach high in the tower. A short time later, the tower ruptured. The violent explosion propelled the top 35 feet of the tower well beyond the plant site. Another piece of the tower sailed 500 feet and hit a storage tank of MNT, setting it ablaze. A 6-ton piece of the tower sidewall flew 1,100 feet and came to rest just 50 feet from a 250,000-barrel crude oil storage tank. A piece of shrapnel nearly hit a 500,000-pound tank of toxic anhydrous ammonia. Metal packing covered in flaming chemical residue ejected from the tower and rained down across the facility and neighboring plants. The explosion knocked down 3 operators who had taken shelter just inside the control room door.
As the CSB found in its 2002 study, and in 10 subsequent investigations, reactive accidents can have serious and tragic results. To prevent these accidents, companies should identify and thoroughly evaluate reactive hazards in their processes. Appropriate emergency pressure relief systems and other design safeguards need to be in place. Companies should also develop effective operating procedures and training programs, and carefully manage any changes to existing processes. Finally, facilities need to plan for possible accidents, including evacuation drills and emergency response exercises.
The most important thing to managing reactive chemistry hazards is that you have to have a thorough and complete understanding of your chemistry under design conditions and also under all foreseeable abnormal conditions.
The main message I have is that we cannot avoid reactive chemical hazards. However, chemical plant accidents involving reactive hazards are unacceptable. The technology and the management systems do exist to produce these products safely.
Much progress has been made in chemical process safety since the Bhopal accident in 1984. But deaths and injuries continue to occur from uncontrolled chemical reactions, and significant gaps remain in federal regulations and industry programs to control reactive hazards. It's time to redouble our efforts to prevent these tragedies. Thank you for watching this CSB safety video.
For more information about the Reactive Hazard Study or other CSB investigations, please visit our website at csb.gov.